Hello everyone, my name is Arik Rinberg. I'm a doctoral student at the Technion Israel, and today I'm going to present mine and Idit's work, a brief announcement on intermediate value linearizability, IVL, a new correctness criterion for quantitative objects. So our motivation and main concern is maintaining and querying analytical counters and data for large-scale real-time analytical systems. So for example, you can see a screenshot of the Flurry system, which provides real-time reports for 830,000 mobile apps with approximately 1.6 billion user devices, all generating data and metadata. But to better understand the motivation, we need to take a simpler example. So as an example, let's use a controller, which we show here as a laptop, and two servers, servers A and server B. And the controller needs to decide whether or not another server is needed. It does so by querying the analytical counter on the servers, showing how many people are currently connected to the server. For example, it reads the counter from server A and sees that 24 people are connected to it. It reads the counter from server B and sees that 18 people are connected to it. It sees that the overall number of people connected to the system is 42. This is less than 50, and therefore the system overall can handle the stress of 42 people, and another server is not needed. But this is all fine and well when things are happening nicely and sequentially. But what happens when things start happening concurrently? So let's say, for example, the controller decides that it needs to check whether or not another server is needed again. Concurrently to this, 6 people start connecting to server A. Server A begins handling these requests and begins updating its inner counters. The controller reads the analytical counter from server A. Server A hasn't yet updated it fully, and therefore returns 24. Server A then finishes handling these 6 people requests. Meanwhile, 10 people begin connecting to server B. The controller then goes to server B and asks it to tell it how many people are connected to it. B finishes handling the connection requests incoming by the 10 new people, and therefore returns the number 28 to the controller. The controller sees that 52 people are now connected to the system. This is larger than 50, and therefore, yes, another server is indeed needed. If we look at the time series analysis of the above example, we can see that what we had is an increment 6 on server A, followed by an increment 10 on server B, with a read happening concurrently to both increments, where the overall counter for the number of people connected to the servers begins at 42 and ends at 58. And what we would like to know is what is the set of allowed return values by the read. So the de facto correctness criterion for concurrent objects is linearizability. Under linearizability, what we basically do is take each operation and boil it down to a single point in its execution. So under linearizability, the read can either happen before both increments, returning 42, in between the two increments, returning 48, or after both increments, returning 58. But what the system really wanted to do is know whether or not it needs to spin up another server. Well, we can see that we end at 58. Therefore, we know that another server will indeed be needed. So what's wrong with the number 52? Or, for example, when we read at the beginning and we saw 42, well, what's wrong with returning 44? We know that with 42, we don't need to spin up another server, so maybe with 44, we don't need either. Well, what's wrong with any of the numbers between 42 and 58? We transition between them when people connect, so we don't inherently know what's wrong with any of these numbers. And this is the motivation behind IVL, where the intuition is we allow the return of any number between two legal numbers. So in the example, we'll allow a return of any number between 42 and 58. Formally, the way we define it is by defining first an altered history, in which we replace the return value of read RI with the value VI. We then take our concurrent execution, build two altered histories, and then linearize these altered histories. The concurrent execution is IVL if there exist values such that for every read RI, the value VI is bounded between values VI1 and VI2, such that VI1 and VI2 are legal return values in linearizations of the altered histories. What this basically means is that there exists a certain linearization of the concurrent history where if the execution were to happen in the order provided by the linearization, then the return value would be VI1 or VI2. but the return value was VI, which is bounded between VI1 and VI2, providing flexibility during concurrent times, while still maintaining a certain notion of correctness in the eye of the system designer. A key feature to IVL is that it provides large flexibility during highly concurrent times. However, if the period is sequential, then IVL executes exactly according to the sequential specification, thus providing high flexibility during concurrent periods, but high rigidity during sequential periods. As an example for IVL, we present the IVL batch counter. It has a share array with n elements. An update adds the number v to my share of the array, so vi gets vi plus v, and a read sums over the array. And to show that it is indeed IVL, we consider the read operation. If we were to take a snapshot of the array at the beginning of a read operation, we would see a certain sum. All the values v are positive. So if we take a snapshot at the end of the same read, each element vi can only increase. Therefore, the sum of the snapshot at the end is larger than or equal to the snapshot at the beginning. Because of this monotonic increase, the sum returned will necessarily be bounded between these two values, thus showing that the batch counter in this current implementation is indeed IVL. Examining the time complexity, we see that the time complexity of the read operation is order of n. I need to sum over all the array, but the time complexity of the update is order 1. I only need to update vi. If we were to try and implement a linearizable batch counter, we show that the time complexity of the update must be omega n. We show this by presenting a reduction from a batch counter to a snapshot object, showing that a binary snapshot object can be implemented from a batch counter. For a binary snapshot object, we know that there's a lower bound of omega n on the update operation, thus showing a lower bound of omega n on the update of the linearizable batched counter. What this shows is that the IVL implementation is inherently cheaper than any linearizable implementation, showing the strength of IVL. To summarize, I presented IVL, an intuitive correctness criterion, in which the values observed in concurrent executions are bounded between legal ones with respect to linearizability. It also allows for cheaper implementations, sometimes inherently cheaper than linearizability. In the full paper, in DISC 2020, we define IVL for randomized objects and show our main theorem, that IVL implementations of randomized objects with bounded error also have a bounded error. Such objects are paramount to implementing high-performance, large-scale analytical systems, thus showing the importance of our main theorem. As an example, we present the count-min sketch and show an IVL implementation of a concurrent count-min sketch. Thank you, and I look forward to seeing you one day in person.